everyone. Thanks for being here tonight.
Thank you for being here.
We're welcoming Dr. Joshua Smith from Cal State Fullerton. He's the primary investigator for the Gravitational-Wave group there, which is part of the LIGO collaboration. He got his undergraduate degree from Syracuse, having grown up in the Adirondacks. Then went over to Germany, University of Hanover, for his PhD, Max Planck Institute and all that. Came back to Syracuse for a postdoc. Now he's at Fullerton. He'll be talking to us about gravitational waves. So let's welcome Dr. Joshua.
Okay, well, thank you very much. Thanks for inviting me, Larry. This has been great. I just had a chance to look around the camp. I think this is awesome. You guys have a lot more resources than we do for teaching astronomy. All the art is amazing. I just went through the life cycle of stars over in the other building. Added some last-minute footage to the talk from Astrocamp. So this is great. I've really enjoyed visiting. I'm going to tell you tonight about gravitational waves. So on the cover here, there are a few things to point out. The first is this very beautiful picture here is a simulation of what happens when two black holes collide, and the colors represent the strength of gravitational waves being emitted in space. And I'll tell you a little bit more about what gravitational waves are in the presentation. So this is from the Albert Einstein Institute, where I got my PhD in Germany. And I'm going to show you some real simulations in the talk. I'm from Cal State Fullerton. People call it Cal State Disneyland, or baseball fans sometimes call it Cal State Omaha because they're going to the World Series quite a bit. And it was a very nice drive up to see you all. I told my wife she should pack a jacket. It's a good thing I did. It was about 80 when we left. So, as Larry mentioned, I work in the Gravitational Wave Physics and Astronomy Center at Cal State Fullerton. So, Cal State Fullerton has a relatively small physics department, but we've decided to focus in some areas. And one of the areas is gravitational wave science. It's a new field, so there's an opportunity for us to make a big contribution from Cal State Fullerton. And we have three young faculty. So all three of us were hired within the last, these guys were hired last year, and I was hired 4 years ago, so we're all relatively new. I am an experimenter, so I'm kind of the dumb experimenter of the group. I can make things happen with electronics and such, but these two, Jocelyn and Jeffrey, are really the ones that know all the gravitational theory. And so, maybe at some point you'll be interested in having them out. Jocelyn Reed is an expert in neutron stars, the hot, dense ash left after the collapse of a massive star. And Jeffrey Lovelace is an expert in black holes. What happens if the star that's collapsing is so massive that it can't even stop the collapse of gravity, and it collapses down to a black hole with a singularity. And so he specifically looks at simulating gravitational waves emitted by black holes that are orbiting around each other in space. So you can learn more about us at fullerton.edu/GWPAC. This is the outline for the presentation. I'm going to talk about what gravitational waves are, what sources of gravitational waves exist, detectors that we're building to try to see these waves. The searches that we've done so far, they've been unsuccessful so far because our detectors weren't sensitive enough, but there's promising news in the status and future arc of the field. It's a relatively small group here tonight, so I'd be happy if you had questions about something, you can interrupt me, so I don't just blow past the topic and you have to wait half an hour to get your answer. But I'm going to get started with Albert Einstein. So here he is as a relatively young man in 1905. And that's when he came out where he discovered this essential law of the universe in his theory of special relativity in 1905, that no information can travel faster than the speed of light. So the speed of light sets the ultimate speed limit in the universe, and we know it as c, 3.0 times 10 to the 8 meters per second, which we can also relate to 186,000 miles per second. So that's how fast light travels, and he said that's the fastest speed there is in the universe. In 1915, he expanded on his special theory of relativity to create the general theory of relativity, which is Einstein's theory of gravity. So we learned about Newton's view of gravity, where you have two objects, mass 1 and mass 2, which could be the sun and it could be the earth, for example, and that there's a force between them that depends on the product of the two masses and is inversely proportional to the square of the distance between them. That's Newton's universal law of gravitation. Einstein's theory of general relativity is more accurate than that, especially for very strong gravity, like around a black hole, or for very high speeds, like when things are moving an appreciable amount of the speed of light. And the key idea here is that gravity is not just an instantaneous force between two objects, but more a curvature of space and time. So gravity is built into space-time. And it also makes some strange predictions, as we'll see. But first, John Wheeler, who was a disciple, came later than Einstein, said in this famous quote, "Matter tells space-time how to curve, and space-time tells matter how to move." So if you think of the solar system, Newton might have thought you have the sun. So Newton's big step was saying that the force that makes an apple fall on Earth is the same force that holds the Earth in its orbit around the sun. And Wheeler and Einstein would think of it like this. The sun has so much mass that it curves the space and time around it. And then the planets are held in orbits, in their orbits by this curvature. So usually at this point in the presentation, I wave my hands around a lot and I try to show what's happening here. But I was just walking around campus with Larry, and he actually has a demonstration of this. So we put in 3 planets here, and you can see that the curvature of the sun object that we put here that's warping the space and time brings all the planets into an orbit. Now, this doesn't act quite like our solar system here, because after a while all the planets here bang into the sun, which isn't what we hope is going to happen to us. So I'll ask the audience, what is the reason why these marbles end up banging into their sun, but we don't? What's the difference in the situations? What's causing these to slow? Friction. Okay. So friction. So when the marbles are moving around, they have energy. They have kinetic energy, 1/2 their mass times their velocity squared. The friction takes away that energy. So it's a way that the energy goes out of the orbit, and the orbit loses energy and it gets smaller and smaller. So in this case, there's friction. If we go back to the solar system case, there isn't. And we're going to come back to that a little bit later. So I'm gonna show this in class now and keep that. All right. So the strangest prediction that comes out of the idea that gravity causes space-time to curve is black holes. It turns out that if you get enough mass in one place, the mass pulls on itself so strongly that it reaches a point where there's no type of force that can stop it from collapsing. In a neutron star, you have all kinds of quantum mechanics like degeneracy pressure and the Heisenberg uncertainty principle that's causing the neutrons to not get any closer to each other. If you have more mass, if you take the biggest neutron star you can make it, you toss a little bit more mass into it, it'll reach a point where there's so much gravity pulling in that not even quantum mechanics can save it, and it will plunge down to a singularity. And what happens is, if you were to do that in Larry's demo, it would be like poking a sharp hole down to the bottom. Space-time would get curved so much that the strength of gravity, which is proportional to the slope of the space-time here, would be so strong that nothing could escape from the inside, not even light. And there's a special place in the curvature called the event horizon, where if something goes inside of that point, it can never escape from the black hole, or we on the outside can never know anything about it from that point. So this event horizon sort of defines the size of a black hole, and it's pretty easy to calculate. Gravitational waves are another prediction of Einstein's theory, his general theory of relativity. Also around 1915, actually the gravitational wave paper was wrong in 1915, and it came out with the right one in 1960, almost 100 years ago. So gravitational waves are ripples in space-time. Let me back this up. The idea is very similar. So if space-time is a curvature caused by mass, you can imagine that if you took those masses and you kind of moved them around, let's say instead of having one sun in the center on Larry's demo, you had two suns rotating around each other. You could imagine you could make some ripples going out. On that surface, it might be a little hard to see, but if you think of doing something like putting your finger on the surface of a pond and going like this, you can imagine that it makes ripples going out. So Einstein's theory predicted that if masses move in a very irregular way, like going around each other like in an orbit, that they will produce waves that flow out in space. And this is a picture of two black holes going around each other and gravitational waves being emitted. And the prediction was that these waves would travel at the speed of light, the fastest speed there is, or another type of information, that they would be generated by objects like things that co-orbit each other, or things that spin like a neutron star, as long as they have some asymmetry, like a little mountain. And that gravitational waves would interact weakly with matter. So unlike light, which gets blocked by things like the Earth, gravitational waves can't be jammed. That's actually a moment to pause to tell you a funny story. NORAD and actually DARPA is DARPA has put out a grant proposal solicitation for essentially a gravitational wave phone, because they've realized that gravitational waves can't be jammed. They can pass right through matter. But as you'll see in this presentation, the big problem with the reason why I haven't got their $1 million to do it is that the smallest gravitational wave phone I can think to make is about 2.5 miles long. So, not very loud. Gravitational waves can't be jammed. They travel through matter, and they're also a new spectrum in which to explore the universe. So you're all astronomers. You know that in astronomy there's this whole electromagnetic spectrum. We can see a sliver of it, but you have radio. I think there's radio. I saw some radio equipment here on the site. Radio and X-rays and gamma rays and all these other wavelengths of light can be used to explore the universe. Gravitational waves are an entirely different spectrum, not just a different wavelength. So I might just be full of crap. How do you know that I'm actually telling you the truth, that these gravitational waves exist? They were predicted over 100 years ago, and we haven't measured them yet. So why do we think they exist? The two people up on the right, their names are Russell Hulse and Joe Taylor. They used this giant observatory to measure two pulsars. And so, first of all, does anyone know which observatory that is? Everybody knows. All right. And what type of light do they look at in Arecibo? What part of the EM spectrum? Radio. That's right, because that's why it's so huge, because the wavelength of radio light is so long, they need a really huge dish. And they also make James Bond movies there. So, visible light is just a part of the electromagnetic spectrum. Using observatories like Arecibo, we can observe the universe in radio waves. Russell Hulse and Joe Taylor did this to see two neutron stars that were going around each other. A neutron star is the dense hot ash that's left after a star's death. It's usually 1 to 2 times the mass of our sun, but it has a radius, and I should have updated this for our location here, but if we were in Fullerton, it would only reach 10 to 15 kilometers across, so Fullerton down to Garden Grove or Orange. Relatively small. The matter inside it is above the density of the nucleus of an atom. And they can rotate up to 700 times per second, so they're really extreme objects. If you want to learn more, Jocelyn Reed, who I work with, is one of the world's experts in neutron stars. So Hulse and Taylor observed this system of neutron stars, and they were able to observe it because one of the neutron stars was spinning and emitting radio waves. So you guys know what type of neutron star that's called? Pulsar. Right. Yeah. So they saw this pulsar, and they were able to see the radio waves being emitted from it. And using the Doppler effect and the timing period, they were able to determine all of the orbital parameters for this orbit. And they watched it. the period is about 7.75 hours, and it's two 1.4 solar mass neutron stars. And they figured out that it's decreasing its orbit about 80 microseconds per year. So it's getting closer and closer as time goes on. And that means in 300 million years, they're going to hit each other, just like the marbles did in Larry's demonstration. So here's a situation where you're out in space and we don't think that there's any friction. Earlier we said that friction was the cause for the energy loss that decreases the orbits for the marbles in the demo. So what is causing the energy loss that's making these two neutron stars spiral together? That's right. All right. So what Hulse-Taylor found was that gravity waves, which carry some energy, are being emitted from the system, and they're making the orbit shrink. And when they compared the orbital change and exactly what was happening with these two neutron stars with what Einstein's paper predicted, they got exactly what it predicted. So they said, this looks like a system that's emitting gravitational waves, and they measured it indirectly by looking at the orbits of the stars and how they were shrinking. So, I just said all that. They found the orbit was shrinking due to gravitational waves, and this agreed precisely with GR's predictions. So this is actually called cumulative shift of periasteron time here. But, and this one is the year. So they observed it from 1975 to 2005, and they found that the orbit was decaying with all these dots here, exactly in agreement with the theory, which is that line, and that's a no-fit data. So these guys, so then they won the Nobel Prize. That was pretty good. So that's why we think they exist. So what are some sources of gravitational waves? Why is this astronomy? So it turns out there's a sort of orchestra of gravitational waves. And I say this because gravitational waves are signals that we would measure in the audio band. So a lot of them have you could put them through speakers and they'd have a noise associated with them, even though what they're really causing is something different. And I've shown them here from whether we can model them well or poorly, and whether we can write down what they should be doing, and whether they have short or long duration signals. So I guess we'll start with the most well-known gravitational wave source. That's short duration signals that are well modeled. And that's the very end of the in-spiral of two black holes or neutron stars when they're going around each other and emitting gravitational waves and getting closer and closer to each other. And I'm going to show a video of this in a second from my collaborator, but basically the two go around, they get closer and closer, and if we played the signal through a speaker, it would sound like... try it again, my lips are a little dry. So it starts very low, and then peaks up. Yeah, pretty soon I'm going to have a dog up here with me. Yeah. My dog's here too, but he was too excited to come. So yeah, we could have played. It would have been fun. Then you have long duration, well modeled signals. So this would be something like a spinning neutron star that has a little bit of a mountain. So if you have a pulsar and it has some kind of mountain on it, that could emit gravitational waves. In poorly modeled short duration things, you have things like star explosions, supernovae. They emit gravitational waves. And then in poorly modeled long duration things, we have background from the early universe. Early in the universe, there was a lot more energy in motion. And so there were a lot of things moving very quickly and emitting gravitational waves, and it was all, you could think of it like a very chaotic water tank, and things were bouncing off the sides and getting very chaotic, and it sort of caused a stochastic background. And we think that a remnant of that is still left over today, although it would be very hard to detect. So these are some sources of gravitational waves. And then this is a video from my collaborator, Jeffrey Lovelace, and his collaboration, the SXS collaboration, Simulating Extreme Spacetimes. They use supercomputers, so giant computers that fill rooms, to simulate what happens when two black holes orbit around each other and smash into each other in various ways. So what's shown in this one, and I'll walk through it again, are two black holes that start isolated. The dark shell around them is meant to show the event horizon. You can see the path of their orbit on the top. Down on the bottom here, this surface is called an embedding diagram. So it's the equivalent of the sheet in Larry's demo from earlier. The colors indicate the passage of time, how quickly time passes. So red means time passes more slowly and blue is normal. And the arrows represent the swirling of space, something like frame dragging. Here, the two black holes merge and they form one bigger black hole, and then it kind of rings down like a bell. The final thing is, you might have noticed while that was playing, there was a little red line going across this. This thing at the bottom is the time series, so it's the amplitude versus time, like what you'd measure on an oscilloscope for the gravitational waves that are emitted from this system. It starts out low frequency for a long time, and then over towards the end, it chirps up really quickly to high frequency, like that. And then they collapse into one, and it rings down. So this is the type of signal we'd be looking for. And yes?
By rings up really quickly, do you mean like 100 million years?
Oh no, so these may go around each other far away in an orbit for millions of years, but this last part here takes a couple of seconds, just like my whistle. So by the end, the black holes are moving a very large fraction of the speed of light, like half the speed of light or something, around each other, and the frequency gets to about 1,000. Well, actually, for black holes, it would get to about 100 hertz, so they're going around each other 50 times a second by the end. And then they turn into one bigger black hole, and that one has some asymmetry, and so it rings like a bell, and still causing gravitational waves, and then it dies down. And so I'll break it down into 3 parts a little later, but that's the main thing. Yeah?
If they each have accretion disks lying around each of them, and
right.
They each have jets going off of their axes,
yeah.
What happens to all that?
Well, the accretion disks and the jets, what that would do would be, it would allow us to observe some electromagnetic associated with it. So the gravitational waves would be altered some, but probably not changed too much, because the majority of the mass is in the black holes. But the really cool thing would be, if something like that happened and it did have electromagnetic radiation associated with it, we could see it with a gravitational wave detector, and we could also see it with a telescope, which would be great. So we could learn a lot more about the system that way. Thank you. Yeah.
So a couple of seconds from the perspective far away from the black hole?
Yes, out in our regular time.
Okay.
So here on Earth, we would measure this signal happening over a few seconds. And then if you want to ask more complicated questions about falling into black hole and time passage and stuff, then you'll have to ask my black hole experts. So I'll quickly get out of my league. All right. So I also teach astronomy at Cal State Fullerton. Larry and I met at the OC Astronomers meeting in nearby Chapman College, and I showed a similar slide here. If you're wondering what kind of systems emit gravitational waves, or which of them are ones that you might know of, or might have seen through a telescope, well, there was supernova 1987A, which is a beautiful supernova, but it's only visible from the southern hemisphere. That would have emitted gravitational waves, and we had gravitational wave detectors at the time, but they weren't sensitive enough to see it. There's also the Crab pulsar in the Crab Nebula. We're actively looking for this the whole time. That's in the Taurus constellation. We have lots of different pictures of that in different wavelengths of electromagnetic light. That's how we found the pulsar. But we haven't found gravitational waves from it yet, although we've set very good limits on how loud they could be, how big the mountain on the Crab pulsar could be. Betelgeuse, I'm sure you all know, this is a future core collapse supernova candidate, so it could blow up at any time. It's only 642 light years away, and so we think that if this blows up, we'll definitely be able to detect it. And then there's Sagittarius A star, the black hole at the center of our galaxy. We've seen stars, we've seen star S2 make a complete orbit around it. We've seen partial orbits for all these other stars, and we're able to calculate that this has a mass of about 4 million times the mass of our sun. This one happens a little slower than we're able to detect with our detectors, but it's definitely emitting gravitational waves. So those are some extreme systems in the night sky. So a few questions that measuring gravitational waves could shed instead of light gravitational waves on. Bad pun, I'm sure. These ones up here, fundamental physics. So what are the properties of gravitational waves? How do they act? Do they travel at the speed of light? Is general relativity the correct theory? And is it valid in the strong gravity conditions? Everywhere we've checked, every experiment that's ever been done has validated general relativity. But we know that there's some place where general relativity and quantum mechanics don't meet. And we also know that there are odd things happening, like galaxies rotating at the wrong rate, which makes us think that there might be things like dark matter. So any test that we can do of general relativity is really important, because at some point we're going to find something wrong with it or one of our other theories. For astronomy and astrophysics, how abundant are black holes? How many are there? Where are they? What causes gamma ray bursts, these very bright bursts in astronomy? What are the masses and structures of neutron stars? What happens in a core collapse supernova exactly? Like, what does the mass do? Is it asymmetric? How does it work? And these are things that gravitational waves could tell us information about. So now we're going to move on to the part where I come in a little bit, gravitational wave detectors. So, Einstein thought of gravitational waves in 1915 and got the right equations in 1916. But as for whether we could ever detect them, he didn't think so. He thought that the effects were so small, it's doubtful we could ever measure them. And to explain why Einstein was such a pessimist about this, we have to look at what effect gravitational waves cause. So I said that they're ripples in space-time. Space and time is like the 3 space dimensions and 1 time dimension all rolled up together. So if you cause ripples in space-time, you change distances. And so as gravitational wave passes, it changes the distances between objects. So if you imagine that I had set up a sphere of little objects here, and a gravitational wave was coming into the board like this, it would stretch the distance along one direction, while at the same time squeezing the distance along the other direction, and just keep going. So this would be what would happen if you had a sinusoidal gravitational wave that just kept stretching and squeezing. So what we want to do is look for small changes between the distances of objects. And categorize how much the change is by something called strain. Strain is the change in length divided by the original length. That's how we characterize the amplitude of gravitational waves. So here we have about, I think, 10 squares. And we're moving it about a total of 2 squares, one square up or down on the top or bottom. So that change in length is about 2, and the total length is about 10, so that'd be about 1/5. And just to round it, I'm going to say that's 0.1, 10 to the minus 1. The reason why Einstein didn't think we could detect gravitational waves is that if you take 2 of those neutron stars or black holes and you rotate them around out in space, relatively, some astronomical distance, but relatively close to us, the strain that they cause on Earth is 21 orders of magnitude smaller than what we see here. So it would be dividing that motion by 1 with 21 zeros after it. And to put that into, let's see if I'm going to put that into perspective. Well, to put that into perspective, if you had a meter stick, it would move 10 to the minus 22 meters, which is pretty useless because we don't know anything that small. But if you had something like a few miles, you'd be talking about it moving 1,000th of the width of an atom. And so these are tiny, tiny motions. So Einstein didn't think we could do it. But again, I'm here today, and so we do think that we can do this. It's just that between Einstein's time and now, we've made a lot of advances in precision metrology, being able to measure things very accurately. One of those advances is a Michelson interferometer. So we built lasers, very accurate wavelength devices that have a very nice light beams. And we can use these to create something called an interferometer. So what happens here is you have a laser, it shoots a beam of light at something called a beam splitter. That's kind of like a mirror where you have half a mirror coating. So half the light goes through it, and half the light bounces off it. And then these two things are called the arms. There's a mirror at each end of them. So the light gets split in two, and it travels down these two arms for some time, and then it bounces back. And when it comes back to this point, the light waves, which are like, if you think of like sine waves, they interfere. So if you have the sine wave, which looks like that, and two of them come back like this, so the crests are at the same point, then you get a type of interference called constructive interference. So they add. You'll get twice as you'll get each of them was half as much light because they went down the two arms, and you'll get back the original amount of light. But if you finally position one of the arms so that when it comes back, the two waves don't line up, but they actually line up a trough to a crest, then all the light coming like this cancels out, and you get no light coming out here. So in the one way, you get all the light coming out here, and in the other way, you get perfect destructive interference. So you hold it so there's no light coming out. And in this situation, you can basically set up something like this and wait for something to stretch one of the arms and squeeze the other one. And if you do that, it shifts from this condition slightly off, and you get a little bit of light. And so this is a machine to transform a little bit of space-time change to a little bit of light at our photodetector down at the bottom. Does anyone have any questions on that? Yes?
What wavelength of light do
We use infrared light at 1064 nanometers because that was the best state-of-the-art type of lasers they had. For us, it's much more important that the lasers are stable and low noise than the specific wavelength.
Okay.
So one bad thing about that is that our laser is, since infrared, is invisible, and it's also 200 watts. So you can invisibly destroy stuff pretty easily. Like, you can burn through cables, and yes, you have to be very careful. Yes.
How do you stabilize the lengths of your two arms so precisely? Because I know I've seen some outputs of ones where it's even the tides going in and out of compressor land enough that it causes problems.
Yeah, for us, the tides are huge. The tides are way huger than the signals that we want. So that's a great question. How do we stabilize the arms so precisely? This is a very simplified drawing, and I'll show you some complicated pictures of some of the things we do later. But the very simple answer would be, we measure a signal down here that tells us how far we are off from our operating position, and we use feedback control. So down here, we compare what we get to 0, essentially, and we have, so if one of these arms moves a little bit, we're able to measure down here which of the arms moved and by how much, and then we just push back on it. And so we hold it in its exact right position all the time with feedback control, and then, to be honest, rather than measuring what comes on the photodiode as our signal, we measure what we have to push on the feedback as our signal. So we have to hold everything exactly in its linear operating point and measure what pushes we do to see the things.
And that gets rid of like the big macro changes, so if you have a signal that's small, you would see that.
Yes, so we have many tiers of forces that we apply. So the tides are so big that we actually have a Newtonian prediction of the tides. The tides stretch the Earth enough for our detector that we have a little computer that just computes how much the ground is moving, and we have hydraulic actuators outside of our system that push the things to, like, if the Earth is expanding, they push the opposite way so that our mirrors don't move. And that's the most coarse actuation. At the very end, we're doing like little nano pushes to get rid of some of the smaller things. Yes.
How much do the tides, like, elongate it or shorten it?
10 micrometers and tens of micrometers. Wow. And because the Earth is, I mean, look how much the oceans go up and down. And the Earth itself is solid, but it has some, what's called a Young's modulus. You can determine how much it will stretch for a certain amount of strain you put on it. And over the distances that we're looking, a couple of miles, it actually stretches, you know, tens of microns or hundreds of microns in some cases, depending on the exact alignment. Yeah, so it's a lot, and we're looking for things that are 10 to the minus 19 meters. So it's bigger. So, and there was another question about...
What's the dimensions of your interferometer?
Okay, we'll come to all that. And there was another question about why do we need a 200-watt laser, and we'll come to that too. So, yeah, get the most power in your laser you can. If you want, so the big thing is, as you guys have probably already started thinking about, if you're looking for something that small, and the last question just led directly to that, how do you isolate from all the disturbances that are way bigger than that? So for one thing, our mirrors are suspended as pendulums. I don't have a great pendulum here, but pendulums have a property that if you so pendulums are a lot like the suspensions in your car. If you move a pendulum at low frequency, the pendulum will move exactly as your hand. But if you move it at the resonance, it will move a lot, while your hand is moving just a little. But if you do something like this and you move it really, really quickly, the bottom of the pendulum almost doesn't move at all. So pendulum can isolate the motion of the thing at the bottom above a certain frequency, or above you know, if you move it fast enough, it won't move at all at the bottom. So we hang our mirrors from tiny strings, and we put those inside vacuum systems, so there's no air anywhere. And those vacuum systems have these giant hydraulic controls that move it around to cancel out things like the tides. And then inside these vacuum systems are even more fine positioning things, tables that these sit on that cancel out the ground motions. And the laser beams and the photodiodes and everything are inside the vacuum system, and then we use servo feedback control to hold everything in its place. And there are hundreds and hundreds of what we call degrees of freedoms. So alignment of the mirrors, pitch and yaw, length of things, and we try to keep them all as stable as possible using feedback. So it's a lot of engineering. And that's how we isolate from outside disturbances. When you put all that together, you get the LIGO observatories. So there are two of them. This is the one in Livingston, Louisiana. So this is down in rural Louisiana. These are all trees. This is what happens. This is what happens if you dig a hole in Louisiana and it fills up with water. So we needed to have these arms be perfectly level, and it turns out that the Earth is curved. And, so we had to dig some fill to make the arm perfectly level. And when we did that, we got a bayou, which was pretty cool. So there were alligators in there, and I used to feed one my lunch. But then it got too friendly to humans and had to be taken away. This is the LIGO Observatory. In this building, we have our laser, we have the beam splitter, we have lots of other optics. It's this picture I just showed is inside that main building. This tube is all a vacuum system. The LIGO vacuum system is the largest in North America, and the vacuum inside it is 10 to the minus 9 torr, which is as good as the environs around the International Space Station. Down here is the end station. It's 2.5 miles away, or 4 kilometers, and that's where the mirror hangs, the end mirror. So the light comes down here, bounces and comes back, and there's another one this way to make that Michelson interferometer. Yeah, there.
So why build it in Louisiana?
Okay, so there are 2 reasons for that. One, it needs to be somewhere rural, because traffic and roads and trains and things like that make so much seismic disturbance it can still hurt our instrument, even though we do all this stuff to quiet it. The second reason is political, but I actually think it's a really good reason. So there were a number of sites that we came up with, and then at that point it became political, like congressmen and senators wanted to get that site for their place. And rural Louisiana has almost no science opportunities. So this place has a giant building over here that's a science center. And very much like here, they work with students, they work with teachers, and there's a lot of training on astronomy and astrophysics and science. And so it's a really great facility for rural Louisiana that wasn't there before. paid for by the national government, the NSF. So I think the reason is because that's a place where it could do the most good, and we could still do our science. There's another one that has a different story. It looks a little different. This is LIGO Hanford, which is in Hanford, Washington. And we got that one cheap because Hanford, Washington is a nuclear reservation, and not a lot of people want to live there. Are you from the Hanford area?
Yeah, my mom actually worked at Hanford when she was growing up.
Oh, okay. At one of the nuclear sites, or?
Yeah. I'm not exactly sure. I know she's from the Tri-Cities.
Yeah.
So she would quickly be like, "Oh yeah, I work in Hanford," and then move on.
Well, I've visited the Tri-City area.
Yeah.
They have nice wine.
Yeah, I do.
Have you been to I went to this, where the Walla Walla and something come together. It's this really awesome gorge. I did some hiking around there.
We gorge at George.
Okay.
Yeah.
So this is a really cool place. I think the desert and the Rattlesnake Mountains have their own beauty. Sometimes it gets snow there and it looks pretty amazing. But it's the same exact facility except for the environs up in LIGO Hanford. So we have 2 of these, and we're looking to build a 3rd one in India. Because it helps for a sky location to have 3 widely separated. This is the current setup of detectors. These are actually a little old now. Worldwide Gravitational Wave Network in 2010. So LIGO Hanford is up here. LIGO Livingston down here. I did my PhD at Geo 600 in Germany here, which is much smaller. It's only 600 meters instead of 4 kilometers. And then there's the Italian-French Virgo detector near Pisa in Italy. And that's also a very nice place to visit. So that's 2010, and we're building some new ones now I'll tell you more about. We observed with these detectors from 2003 all the way until 2010, and now they've been taken offline to build 10 times better detector that's a lot more sensitive. And we expect that to come online in late 2014 and in early 2015 to start its first science run. So that's why this is actually the most exciting time to be in this field that we've ever had. So, yes?
How are they making them more sensitive? Are they just increasing the distance by 10 times?
Okay, so this has to do with why the powerful lasers and why we're not increasing the distance at all. So it'll be helpful if I tell you now what limits our sensitivity. So this is what limits our sensitivity. This is another picture of LIGO, but now I've increased the detail level 1 step. Now we have a laser, and we have the beam splitter mirror, and we have the 2 mirrors that we originally had. But now we've inserted some extra mirrors here. These mirrors are used to form an optical cavity that bounces the light back and forth many times, which ends up making our arm seem longer than it actually is by the number of times that it bounces. So what is the limit for this in terms of sensitivity? Now I'm going to show, this is a plot. I'll just walk through this. Along this axis is the strain sensitivity in some strange units. As you go down, we get more sensitive. So what we'd like is to get more sensitive. We'd like to get as low on this axis as we can. Along this axis is frequency. So you could think of this as the frequency of the stars going around each other, for example. If they go around 1 time per second, that would be at 1 hertz, which is over here. And as you can see, this keeps going up here. So for this detector, we have no frequency at 1 hertz. At 10 hertz, also not very good. But at 100 hertz, so that means if stars are going around each other 100 times a second, actually it turns out to be 50 times a second that leads to that. That's where our detector has its sensitivity. The sensitivity curve is shown in black. So anywhere above this are things that we can measure. To increase our sensitivity, we'd like to make this curve go down. So what I want to say are the main things that limit how sensitive our detectors are and what stops it from going down. The first is, as we've already talked about, the ground motions shake our mirrors. And we isolate our mirrors with these hydraulics and then with tables and feedback, and we put them on suspensions. But it turns out we can do this better at high frequency than we can at low frequency. The ground moves so much at low frequency, and we just can't isolate it well enough for these initial LIGO things. So the seismic shaking makes a wall over here and means that we can't see any systems where things are moving less than or slower than about 50 hertz. So that means from that video that I showed earlier, we'd only get to measure the last part of it where it's making a relatively high-pitched sound. Now, this one's pretty cool. The mirrors of LIGO are made of molecules and atoms, and those molecules and atoms have a temperature, and from thermal physics and statistical mechanics, if something has a temperature, it means that it's moving. So temperature just means kinetic energy. And so if the molecules have kinetic energy and they're moving, that means that they're not sitting still, and that makes it hard to measure something like 10 to the minus 18 meters. So the thermal vibration of our mirrors sets a limit over the most sensitive frequency band. The way that we make this better is by making our beam spot larger. Because if you look just at one molecule, it's zipping all over the place. But if you make a very big average over many, many molecules, your average gets relatively close to zero, because some are moving forward and some are moving back at any given time. The closer you can get it to zero, the more easily you can see a gravitational wave. So we have pretty big mirrors with pretty big spots on them. The third one is called shock noise. You could think about that quantum mechanically, but I'm not quite smart enough, so I think about that classically. And I think about it as if you're trying to measure zero light or very little light, you're just getting some photons. But those photons come like rain on a tin roof. They're like a statistical pitter-patter falling on your photodiode. And that doesn't allow you to make a very accurate measurement because you only get some here and some there. And this type of noise that it causes is referred to as shock noise, and that's what sets the limit up here. So the way we can make our detector more sensitive is going to be the last part of my talk, but it's addressing these three types of noise.
Is that the same thing as dark current?
Yeah, dark current is shock noise,
Yeah.
but it's electrons.
Yeah.
So it's you have shock noise is associated with the amount of electromagnetic power you have on your detector, and dark current says because there's some thermal noise across your electronics, some electrons are going to flow, and you're going to get a current even when nothing's connected up.
Yeah.
But it's exactly the same process and exactly the same math. So there are also time-dependent disturbances. The one I just showed just sets the overall average. But you can also imagine that if we're looking in our detector outputs time series up here, you can also imagine that things like wind, like if we got a bunch of wind blowing against the buildings, it could make something funky happen in our detector. Or if a plane flies over or there's lightning strikes, we might see it in our microphone, and that might also show up in the detector. So we instrument the detectors with tons of sensors, microphones, seismometers, wind stations, things like that, and then we can use those to isolate and remove some of the things that we know aren't coming from astrophysics. Alright, so searches for gravitational waves. This one's going to be kind of quick because it's getting a little stale. Because we're all getting really excited for the next searches for gravitational waves, and the previous searches were unsuccessful because we didn't have sufficient sensitivity. But I'll tell you a little bit. Earlier I said that the two black holes or two neutron stars going around each other cause this type of waveform. We call it a compact binary coalescence. So you can imagine for about 20 minutes the thing is doing something like this. After it's for millions of years not done very much at all except go around each other. For 20 minutes, it kind of increases in amplitude and the orbit shrink until it reaches this boundary here called the innermost stable circular orbit. So it's going around in an orbit about its center of mass until this happens. And at this point, the two black holes kind of come together like you saw in the video, and you get some kind of craziness happening as they start to merge. After they merge, there's some deformation, and this loses energy like a bell. And so this is called a ring down. And so we have searches that calculate these waveforms very specifically, and then look for exactly that in the data. So we say we have a binary black hole system, and we calculate that it's going to have a waveform like this. And then the challenge of that is that this waveform might be embedded in our data at this level. It might be really, really small, and we have to dig it out of our data. And so we use a method called matched filtering. And it does something like this. If you look at the time series, we run an algorithm on it, and it basically says, I don't see anything, I don't see anything, I don't see anything. Oh, that might be something. And gives us a spike about where this happened. I don't want to go into this too much, but what I do want to say is matched filtering is what your brain does when you're in a crowded room and someone says your name. So you can pick out your name because you know it and you've heard it a whole bunch of times. And our computer algorithms can pick out these signals because we're able to calculate them accurately and we can look just for that thing. So that's what we did. And I was working on a new slide for this, so I'm just going to wave my hands about this. Before we did this search, we were asking, what should we see? So we asked the question, how often do these compact binary mergers happen in a galaxy like ours? And from astrophysics, we can figure this out of all these different observations of different types and set some limits on it. Neutron star happens about 100 times, which sounds good, until I put the units on it, which is per Milky Way equivalent galaxy, which is an actual unit. So, in a galaxy like ours, this happens about 100 times. The problem is per billion years. So, in order to detect these things, we have to look outside of our galaxy. We have to look at many galaxies, preferably like a million. And then, how often do we expect to see coalescences with initial LIGO, the one that we built before that is now being improved? For neutron star, we expected to see about 0.02 per year. So this tells us that we weren't looking at a million galaxies. We were looking at thousands or something, but it wasn't enough. So we expected to see 0.02 per year. So if we waited 50 years, we might be able to see one. But better than that, we ran for a while. We achieved, this measures how far into the universe we could see, and this is the calendar days, it's about 400 days of observing, and so we could see about 100 million light years out into space, but we ended up getting about 10 to 100 times less, lower detection rates than we would need to see something. So, said a different way, we didn't see anything. There are no candidate gravitational wave signals from these searches. So that was from initial LIGO. We could tell that we could look quite far out into the universe, but we weren't able to see any gravitational wave from these sources. All right. So we also did searches for things that we don't know that much stuff about. Astrophysical bursts, like things blowing up, core collapse supernovae, mergers, cosmic strings, glitches of neutron stars, and just the unknown, things that we don't know. We cast a wide net looking for these, looking for things like what's exploding up there, looking for things that are short, less than 1 second, and we also didn't find any astrophysical bursts. We did test something that I think is going to prove to be really useful in the next 10 years, and that's multi-messenger astronomy. We came about this earlier. So the idea is, if there's an accretion disk around a black hole, or if two neutron stars slam into each other, that should make both gravitational waves and electromagnetic light. With multiple gravitational wave detectors, we can triangulate the position and tell telescopes to point in that direction and see what they see. Alternatively, telescopes can say, hey, we think we saw something really interesting at this region, can you guys go check your data? So over the last few years, we started this with our externally triggered and lookup searches. Those are going in the two different directions to try to find sources that were both EM and gravitational waves. We looked at our low threshold triggers, which we thought were probably noise, but we checked them out anyway. It laid the groundwork for doing this. We took lots of telescope photos of things, but we didn't find anything from this either. But we feel like it was really useful, and we're going to be using it more in the next few years. All right, here's one example of what we did with that. People think that short gamma ray bursts, which are very easily observable with things like the Swift telescope, gamma rays don't pass through the Earth's atmosphere, luckily for us, very well, but we can observe them with telescopes in space. And gamma ray bursts are observed all the time, and they're really, really bright. People think that neutron star mergers are a predecessor, are what causes these, are one possible cause. So there happened to be one in 2007 that its position coincided with the Andromeda galaxy, which is only about 700 kiloparsecs away. So we ran a search looking for binary neutron star in spirals at this point, and at the time of the observed burst. And we didn't see anything. We excluded at 99, greater than 99% level there could be a binary merger system in that galaxy. And so this led to some other astrophysics and some other propositions for what that could be. But it wasn't a binary neutron star merger, which is too bad, because then otherwise we should have been able to see it. All right, so that was the searches. And I want to talk more about the status and the future of the field. And I'm running out of time, about 53 minutes it says. So Advanced LIGO is the project that I'm working on. That's LIGO 10 times better. But there are other things. So we're planning to build a detector in India. There's Advanced Virgo, the Italian-French project. There's Kagra, which means Music of the Gods, Japanese project happening at the Kamiokanda mines in Japan. There's the idea of using pulsar timing. There's LISA, which is a space-based version of LIGO that's a little bit mired in funding problems at the moment, but we hope will fly. But I'm just going to talk about Advanced LIGO. And what's happening right now, every day, when I'm looking in on this or when I visit the sites, are things like this. So people are dressing up in bunny suits, and they're putting big, awesome hardware that's better than the hardware I showed you into the detectors. The mirrors are bigger, so we can reduce the thermal noise. The mirrors have more pendulum stages so that we can reduce the seismic noise, push that wall down to lower frequency. So this picture is showing one of the LIGO mirrors here in its big frame, which we call a catcher. It's suspended from another pendulum up here, which is suspended from another pendulum up here. And these guys are working on installing it. This is an auxiliary, this is another mirror with an auxiliary laser that's at a different frequency that we just use for a different type of length control. So it's getting very complicated and hopefully very sensitive. This is another picture of some of the different mirrors. This is one of the complicated points where we have a few different mirror suspensions. I say mirrors, these all look clear to you, but those are mirrors at infrared wavelengths. We can see through them, but at infrared the light bounces off. And it bounces off like 99.99%. They're super mirrors. What we're trying to do is listen for new astronomy. We're listening for these gravitational wave sounds. Even the catastrophically violent events produce tiny signals on Earth. So it's like being at a crowded party and listening for a faint tune. You'd really like to hear it, and what we're trying to do is go around to the party and make everyone be quiet. We're trying to make our suspensions be quiet, the Earth be quiet, everything. It's really hard, but if we can make them all be quiet, we'll be able to hear this Einstein symphony. So we're reducing the mirror motion. This is a picture of the quadruple pendulums we're adding. Yeah, they're pretty amazing. We're reducing the thermal motions by making the mirrors larger, by suspending everything from glass fibers, which actually have less thermal motion. And we are reducing quantum laser noise by going up to 200 watts. So it turns out, someone asked earlier, why do we need a 200 watt laser? This shot noise, the pitter-patter, it increases as you turn up the laser power, the noise, but it increases as the square root of the power. As you turn up the laser power, the signal that we measure increases as the power. So if one increases as the power, that increases faster than the square root of power. So the more we can turn up the laser, the better, which is a great thing to be able to say to funding agencies. Like, the more power we get, the better. So we're eventually going to go beyond the standard quantum limit, and we're using things like squeeze states of light to do quantum mechanical manipulation of the uncertainty principle. I don't have enough time to tell you about it today, but that's the kind of stuff we're doing to go to the next step. So when are we going to hear gravitational waves? Advanced LIGO is about 100 times, let me see if I have a better one. Yeah, let me go to that. Advanced LIGO is about 10 times more sensitive than initial LIGO. That means we can see 10 times farther. But 10 times farther, being able to see with a detector is something like this, ends up being 1,000 times the volume. Because you get 1,000 times as many galaxies within that volume that you can see. So by making a 10 times improvement, we can get 1,000 times the volume of the universe, and we expect that per year, we should see neutron stars about 40 per year coming up in the next few years. 2015 is going to be the first step of that, but we think 2015 to 2019 we're going to be making detections of these. And it should be a really exciting time. So expect to see about 40 neutron star coalescences per year. Summary, the initial LIGOs reached their design sensitivity, but we didn't detect anything. Advanced LIGO construction is underway, and we expect several detections per year to begin as soon as 2016, which is a real push for us because it's exactly a century after Einstein made the prediction. So we hope to make a detection for the centennial. It's going to be close. We hope it's close. The future of gravitational wave astronomy is really bright. So, and that's the end.